have the conference.
So I think it's time to start the last session of this conference. And the first talk will be on critical phenomena in H-flavor QCD.
Okay, so first of all, I thank the organizer for giving me this nice opportunity. So today I will talk about the critical phenomena in H-flavor QCD, which is motivated by the beyond standard model. And this work is in collaboration with the lab KMI collaboration. So although now I am in Marseille, Marseille University, I have a second position in KMI. And as you know, the Higgs boson is discovered, and the LHC second run has started. So now it is time to investigate the physics of Higgs and electroweak symmetry breaking. So there are three basic questions. The first one is what is the physical contents of Higgs? And what is the physics of the electroweak symmetry breaking? And also how we address the fine-tuning problem for the Higgs sector. So a possible answer is that the Higgs is the composite particle, analogous to the QCD sigma particle and Cooper pair in the superconductivity. And the electroweak symmetry breaking is realized by the chiral symmetry breaking of the new strong dynamics. So here F indicates the clock, not the standard model clock, but strongly interacting new fermions. And in this case, we do not have the fine-tuning problem. So let us remind of you the usual QCD, chiral symmetry breaking. The chiral symmetry breaking plays an essential role to explain the mass spectrum in QCD. So we ask that, for example, can we identify the QCD chiral condensate for the scalar mode to be Higgs? Of course, as you know, this is not the case, because in this case, the W and Z boson mass becomes too small, at most 30 MeV. So we can consider the scale-up version of the QCD. Let us call it here QCD prime. So simply is QCD is scaled up to 100 GeV. Then can we consider the Higgs in this theory? Maybe no, because as you know, the scalar mode is much heavier than the pion mode and much larger than the comparing to the scale of F5. So Higgs becomes too heavy in this theory. So to solve this problem, we consider the many flavor QCD, which have a novel working dynamics. I will explain what is the working. So let us consider the response of the system to the energy variation, which is characterized by the beta function. So in the QCD case, the beta function is, as you know, negative, and then the stringy interaction appears. But if the number of flavor is increased from 3, then the two-loop beta function tells us that the second zero appears. This is called Banks-Zaks infrared fixed point. So according to this fixed point, the running coupling stops at a certain value here. And in this region, the coupling is insensitive to the change of the energy. In this sense, the conformality is dynamically generated. Then, beyond the perturbation theory, the Schwinger-Dyson equation indicates that such infrared dynamics is spoiled by the non-perturbative chiral symmetry breaking. Accordingly, the running coupling is something like this. So here, approximate scale symmetry emerges, which is called walking. And eventually, such approximate symmetry is broken by the chiral symmetry breaking. So this chiral symmetry breaking simultaneously breaks the scale symmetry. So the scalar part appears as a so-called technidilaton, which is a pseudo-Lamb-Goldstone boson for the scale symmetry breaking. However, this kind of consideration heavily rely on the Schwinger-Dyson setup. And recently, the running coupling in many flavor QCD is extensively investigated in the lattice community. So actually, we do not know much about the many flavor QCD. In this talk, we focus on the 8 flavor QCD using lattice gauge theory with Monte Carlo simulations. So this 8 flavor is motivated by the so-called the simplest technical model called one family model. And we investigate the chiral symmetry breaking in 8 flavor and or conformal or walking dynamics. So and then we investigate the critical phenomena associated with the infrared fixed point characterized by the mass anomalous dimension gamma. So this critical phenomena shares the interest to the finite temperature QCD or finite density QCD. Such a viewpoint is investigated in many works from Milansky-Yamawaki study and based on Schwinger-Dyson and Brown-Giat study of the functional normalization group and also several lattice gauge theories. Okay, so this is a brief introduction for the many flavor QCD. So I will show the main results. Okay, so our observable is the mass spectrum, hadron mass spectrum, which is a function of the lattice spacing A and the lattice box size L and the probe bare fermion mass MF. So in our case, we have the data for only one lattice spacing. And in this talk, we investigate the volume dependence and also the mass dependence. And then, for the obtained mass spectrum, we analyze that assuming the chiral perturbation ansatz and the finite site hyperscaling ansatz. So let us start first from this chiral perturbation ansatz. So this is a pion decay constant in 8 flavor QCD as a function of the bare fermion mass. Here the pion decay constant is defined in the same way as the usual QCD here, in this way. And we fit the spectrum data by assuming the chiral perturbation form. Then, as you see, the fit works with a reasonable chi-square. And also, the intercept is found to be finite, indicating existence of some scale, breaking the scale symmetry. Then, in lattice units, this value is found to be this number, and this number is identified with the electronic scale. So this is a scale setting in our theory. Then this is again the chiral perturbation fit of the low meson mass. This again works, and we have a non-zero intercept. And by using the scale setting scheme explained in the previous page, for example, we have this kind. We find the low meson mass values in this way. So this is also the ambiguity is still very large. This is one of the prediction from our lattice results. Then last year there was the announcement of the 2TB excess around 2TB diboson, and we are very much excited. Okay, yes, excited from these results because this can this has a possibility to explain that, but unfortunately, as you know, this excess is almost disappearing. So this is a ratio of the decay constant F pi over pion mass. As you see, the pion mass, this ratio becomes larger towards the chiral limit. This indicates that the pion mass becomes lighter towards the chiral limit. So the theory seems to have a chiral dynamics. And one of the striking results is the mass for the scalar singlet. So here plotted is the mass of the sigma, so-called sigma in H-flavor QCD for various volumes. And that's compared to pion. And as you see, that mass of sigma is comparable or even smaller than pi. So this indicates that the sigma is very light comparing to the standard QCD case. So this implies the technidilaton nature of the sigma. And in order to obtain the chiral limit value, my collaborator developed the so-called dilaton chiral perturbation theory, whereas in addition to the so-called chiral field, another field corresponding to the scale symmetry is introduced. And then we expand the obtained effective action in terms of the pi and sigma, and then read off the coefficient of their quadratic term to obtain the mass. And then we obtain this kind of formula. Here, the blue one is a fit parameter. By using this fit, we obtained estimated the value in the chiral limit. But unfortunately, this is consistent to 0 with large error. But the point is that this value includes this number, and this number is necessary to explain the 125 GB hits. And also, from the fit, we can predict the dilaton decay constant. Okay, so let us go to the finite size hyperscaling analysis. So this is the main discussion, main part of my talk. So instead of the chiral perturbation ansatz, now we adopt the different ansatz, so-called finite size hyperscaling ansatz. So let us consider the autonomous spectrum normalized by the lattice box L. So the renormalization group analysis dictates that this combination scales as this scaling parameter x here, written here. And also, if the system is slightly deviate from this infrared fixed point, this function may also depend on another irrelevant operator. But this is very small correction. So sufficiently large x around the infrared fixed point, this function is reduced into this simple form. Or if we include the correction term, this function is something like this. So we fit our results, mass spectrum, by assuming these fitting formula. Then the question is, does the mass spectra in H-flavor QCD respect this finite size hyperscaling with universal gamma? If this is the case, the theory is performed. And if this is not the case, that indicates a broken chiral symmetry. Or some other contaminations. For example, this X was not so sufficiently large, or probe mass is too large and explicitly breaks the conformal symmetry, or we are still very far from the infrared fixed point, and irrelevant operator effect dominates. So let us investigate our spectrum. Then we find this is a hyperscaling fit. And then we find that all mass spectra looks aligned. This is very different from the 4-flavor QCD program. In the 4-flavor QCD case, this kind of alignment never happened. So the 8-flavor QCD is something different from the usual QCD. However, we can evaluate the mass anomalous Mendel gamma from the fit. As you see, so this is a collection of the gamma for various operators. We find that the gamma is not universal in 8-flavor QCD. And sometimes the chi-square over the UF becomes crazy. So in this sense, 8-flavor QCD may be something different from the conformal. In fact, if we impose the universal gamma, then and we fit all spectrums, assuming the finite size hyperscaling adapts, then if the fit is perfect, the data should align this on single line. However, as you see, it's very much scattered, and actually the chi-square over the UF is very bad. But if we include the correction term indicated by the renormalization group argument, then fit drastically the fit quality drastically becomes better. So, okay, thank you. So here I would like to go to the discussion. Our findings are as follows. First, in the chiral perturbation analysis, we find that the increasing nature of this ratio, this indicates that the chiral broken nature. However, simultaneously, the data can be beautifully fitted in the finite size hyperscaling analysis, including the correction term. So, it is very difficult to say that the theory is conformal or chirally broken. But at least we have to consider how these two figures are compatible from the same data. Let us consider this question. Then, in order to investigate that, we consider this kind of ratio. Here, the denominator is just the fit answer itself. So it's the same as this one, fit function. And the numerator is the correction term. So this RH and ratio RH measures how the correction term larges in the finite size hyperscaling. So you find that for the pion case in particular, the correction term becomes almost 50%. So in other words, this kind of, although we have achieved the beautiful alignment, in this fit, the 50% correction appears as a pion mass scaling. So in this case, this scaling variable is not dominant anymore. So it is very suspicious that whether we can say that this is really the conformal scale. And why the pion, only pion, specifically scales different from the others. This actually implies some broken chiral symmetry. Then, so that's why we have observed this kind of increasing trend, because M pi and F pi obeys a different scaling property. But it's fair to say that it's premature to conclude the chiral broken scenario also, because this kind of increasing trend can be still explained by within the conformal scenario. Okay. So let us consider this ratio and multiplying the size L, box size L, and assuming the finite size hyperscaling, we obtain this kind of form. And let us consider the derivative of this values. And then we find that this value shows actually the increasing nature towards the chiral limit because of this two exponent. But the second line will disappear because this x is very large. But because of the correction term, this term survives. So this can explain this increasing nature. So I would say that so we cannot exclude the possibility of the conformal scenario. So in this way, it is very difficult to say that chiral broken or conformal. But this is not bad news because that means that 8 flavor QCD is really near the border of the chirally broken and conformal places. So this is this indicates that 8 flavor QCD is really the candidate for the theory having the so-called working dynamics, approximate conformal dynamics. And we show that the right sigma appears in the 8 flavor QCD, and the mass anomalous dimension is very large. This is also necessary condition for the so-called working technical model. So the 8 flavor QCD can be a viable candidate of the working technical model. And also, it's really a frontier of the gauge theory. So we are, as a future perspective, we have to consider the smaller fermion mass and larger lattice and several lattice spacings. And these topics are work in progress. Okay, so thank you very much.
Thank you very much for the talk. Are there any questions?
I think I really like that you showed the difference of the relevant contribution to the whole thing, because this reminds us of the point that the finite size scaling approach relies on Taylor series expansion around the critical point, and usually we just keep the leading term. And yet if the leading term is that big, then you can't neglect the higher order terms, and so so it's really hard to draw a conclusion when you're not close enough to the infrared fixed point that you really see that corrections are small, and you can rely on the Taylor series expansions.
Yeah, okay. Yeah, I agree with you. And first of all, in our data, for example, this one, so we have actually the data in this region. And we find that maybe you know that there is a different slope here. So we carefully discarded such kind of data and carefully did finite volume investigations. So in this sense, at least approximately, we have obtained the most important dynamics of the 8 flavor QCD from this analysis. But also, I agree with you that, as I stated explicitly here, the renormalization must be considered in the plane of the gauge coupling and mass. And that's why we have to consider this kind of, we have to extend our parameter space in this way. So that's the future.
Okay, because of time, we should move on. So let's thank.
Okay, thank you very much.